All right, on to 5.6. 5.6 is where a lot of the stuff, actually, it's where all of the topics that we've been talking about the entire semester come together. But in particular, it's where a lot of the stuff from this chapter that we've been talking about with the area thing and the rectangle thing and the antiderivative thing, it all comes together here when we talk about the fundamental theorem of calculus. But even more importantly, the fundamental theorem of calculus ties together integration and differentiation, which are like the two major themes of calculus. So it's a really cool section. It's a really cool topic. Let's get into it. So first of all, fundamental theorem of calculus has two parts. And the first part says that if f is continuous on a closed interval ab, and if capital F is any antiderivative of lowercase f on that closed interval, then the integral from a to b of f of x dx is just capital F of b minus capital F of a. Now, let's talk about why that is. I'm not going to walk through a formal proof of this with you. You can find one in the textbook if you're interested. But just based on our discussion in this chapter so far, this should make some intuitive sense, and I'll walk you through why that is. So way back in 5.1, we discussed how if a of x is the area under the graph of f from a to x, right? So if we can come up with a function that describes the area under the graph between a and x, then a prime of x is f of x, right? That is, a of x would be an antiderivative for f of x. You should also note that a of a should be 0, okay? Because again, a of x is the area under the graph between a and x, and so a of a would just be the area between a and a, right? Which would of course be 0. And then if we just let a denote the area over the entire interval from a to b, then a of b would equal a, right? So now putting all of that together, since a of x is an antiderivative of f of x, then the capital F of x that we're talking about up here in the statement of the theorem, it must be a of x plus c for some constant c. Now, note that capital F of b minus capital F of a, well, that's going to be a of b plus c minus a of a plus c. And the constants will cancel off, see, right? C minus c is just 0. And a of b is a of a is 0, a minus 0 is just a, right? So f of b minus f of a is the area. It's the area under f of x between a and b. Well, that's how we defined the definite integral, right? So f of b minus f of a is equal to this definite integral from a to b of f of x dx. So that's part one of the fundamental theorem of calculus. And just to kind of warn you of some notation that I'm going to use, we sometimes write f of x from a to b, right? We write this as f of b minus f of, instead of f of b minus f of a, right? And so you'll see why that comes in handy as we go through some examples. So let's evaluate some definite integrals. And the nice thing now is that instead of having to evaluate these integrals by either doing the crazy like rectangle thing and then taking limits as n goes to infinity and all of that work, we can now evaluate these definite integrals just using the fundamental theorem of calculus, which means we can find an antiderivative and then, plug in the limits of integration. So let's evaluate the integral from 1 to 2 of x dx. So what I'm going to do is, first of all, I'm going to find an antiderivative for x. Okay? And that's pretty easy. You add 1 to the exponent and then divide by the new exponent. So it's x squared over 2. so if I were just evaluating the indefinite integral, right, of x dx, then I would say the answer is x squared over 2 plus c. But as we saw up here, the c's are going to cancel off whenever we plug in the limits of integration anyway. And so we don't need to say plus c anymore. But what we do need to do is evaluate this from 1 to 2. And what that means is that we're going to plug in 2, and then we're going to plug in 1 and subtract those, right? So this is going to be 4 over 2, which is 2, minus 1 over 2, which is 1/2. So that's 3/2. And there you go. So the area between the graph of f of x equals x and the x-axis over the interval from 1 to 2 is 3/2 square units, right? So that's the meaning of that. Let's do another one. Okay, so integral from 0 to 3 of 9 minus x squared dx. Alright, same thing. I'm going to find an antiderivative. In this case, that's going to be 9x minus x cubed over 3. And then I'm going to evaluate that from 0 to 3, which means I'm going to first plug in 3, and then I'm going to plug in 0, and I'm going to subtract those results. So this is going to be 9 times 3 is 27, minus 3 cubed is also 27, minus, and when I plug in 0, I'm just going to get 0 minus 0. Alright. So that's 27. 27 divided by 3 is 9, right? So this is 27 minus 9, which should be 18. And there's our final answer. So so this makes things really nice. I mean, imagine like splitting this up into n rectangles and then finding the height of each rectangle and taking the limit as n goes to infinity and all of that stuff that we did before. Remember how long that took us? Well, now it's really quick and simple. It also allows us to do more complicated things than what we've done in the past. So let's see if we can evaluate this one. So again, I'm going to find an antiderivative for cosine. Antiderivative for cosine is sine, right? Because the derivative of sine is cosine. And then I just need to evaluate that from 0 to pi over 2. This is going to be sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1. Sine of 0 is 0. So this is 1. Okay. So hopefully you're starting to appreciate the power of the fundamental theorem of calculus. It's pretty nice. Let's do this one. Antiderivative for ln of x. I think I didn't mean to do this. I think I meant to say that one I think is a little more challenging. Well, you'll learn how to differentiate, or you'll learn how to integrate that in Calc 2 in your next calculus class. But I think this is the one that I intended actually. And I've kind of given it away because I wrote down ln of x already. But yeah, the antiderivative for 1 over x would be ln of x, right? Because the derivative of ln of x is 1 over x. So anyway, that was silly, wasn't it? Oh, and actually I should have absolute values, right? Absolute values around the x. Antiderivative of 1 over x is ln of absolute value of x. Okay, cool. So now this is going to be ln of absolute value of -1 minus ln of absolute value of negative e. Absolute value of -1 is 1, and ln of 1 is 0. Absolute value of negative e is e, and ln of e is 1. So this comes out to -1, which is interesting, right? If you're thinking about this, like an area, here you're getting a negative area, and so you might think, what in the world is going on? Well, remember, the integral is not exactly the same thing as the area. It's the net signed area. We'll talk about this in a little bit more detail here in a second. But yeah, so this isn't quite the area, it's the net signed area. So we'll talk about that a little bit more. Let's do another one. Integral from -1/2 to +1/2 of 1 over square root of 1 minus x squared dx. Go ahead and give the video a pause, see if you can work this one out. Okay, here I go. I'm going to go ahead and solve it now. Antiderivative for this thing is sine inverse, right? This is sine inverse of x. And we're going to evaluate it from -1/2 to +1/2. So that's going to be sine inverse of 1/2 minus sine inverse of -1/2. Now, sine inverse of 1/2. Sine of what angle equals 1/2? Pi over 6, right? So this is going to be pi over 6. Sine inverse of -1/2 would be negative pi over 6. So pi over 6 minus negative pi over 6. It's pi over 6 plus pi over 6, 2 pi over 6, right? Pi over 3. Good. So that's the idea behind Fundamental Theorem of Calculus Part 1. It's very, very useful. There are a couple more things to say. So first of all, note that let's say that you had an integral from 1 to 1 of x squared dx, right? Something like this. Now, we talked, what section was that? I think 5.4. We talked about the fact that if your limits of integration are the same, then that integral should just be 0. Okay, so we're already expecting to get 0 here, but to show you why you would get 0, I mean, you could go through and use the fundamental theorem of calculus and find an antiderivative. That's going to be x cubed over 3, and then you're going to evaluate that from 1 to 1. That means first you're going to plug in 1, and then you're going to plug in 1 and subtract. Well, obviously, you're going to get the same thing. So you're going to get 0, right? Just like you expect. And then the other thing that I wanted to say real quick is that let's say that your limits of integration are backwards, so that your lower limit is larger than your upper limit. And let's do this for something like x squared times the square root of x dx. Now, another thing that we talked about in the same section where we talked about this thing is that you can just switch the limits of integration so that this is the same thing as negative. So it should be the same thing as negative integral from 0 to 4 of x squared times the square root of x dx. But it's not necessary even to do that. Fundamental theorem of calculus will take care of this. So let's do this. Before I try to find an antiderivative, I'm actually going to combine these. This is x squared times x to the 1/2. So if I add those exponents, I should get 5 halves, right? So this is the integral from 4 to 0 of x to the 5 halves dx. And now I can find an antiderivative pretty easily. It's going to be x to the 7 halves divided by 7 halves. Which I guess I could simplify further and call this 2x to the 7 halves over 7. And then I'm just going to take turns plugging in 0 and then plugging in 4 and then subtracting those things, right? So I plug in 0, I'm just going to get 0, right? And if I plug in 4, then I'm going to get 2 times 4 to the 7 halves over 7. 4 to the 7 halves. Square root of 4 is 2, and 2 to the 7th power, holy schmoly. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. 128, I think you get. Oh, and then I have to multiply that by 2, so you think you get 256. 256 divided by 7. So you should get negative 256 over 7 as your final answer. Check my arithmetic there, but I think that's correct. Okay, you would get the same exact thing if you did it this way, because what your antiderivative is still going to be x to the 7 halves divided by 7 halves, but you're gonna evaluate it from 0 to 4, right? So you're gonna plug in the 4 first and then the 0 second. So you're gonna get this minus 0, and so you're gonna get a positive 256 over 7, except that this negative sign on the outside is gonna make it negative after all. And so you're gonna get the same thing, right? Okay. A couple more things to say about Fundamental Theorem of Calculus Part 1. So, as I mentioned a second ago, if f is not always positive on the closed interval ab, then this integral, this definite integral, is not the area between f and the closed interval ab, but rather it's the net signed area. Okay? And, you know, that's because this integral was defined to be the limit as n approaches infinity of the sum from k equals 1 to n of f of xk star, right, times delta x, right, that whole thing. Well, if f is negative in some places, then f of xk star is going to be negative sometimes. And so you're going to end up subtracting stuff whenever f of x is below the x-axis. You're going to end up subtracting stuff off, which doesn't make sense if you're looking for the actual area, right? And so to distinguish between the net signed area and the actual area, I'm going to call the actual area the total area, right? So the total area for a function that's not always positive is going to be the integral from a to b of the absolute value of that function. Okay? So if you're ever asked to find the net signed area, well then you just do the definite integral. Use fundamental theorem of calculus, no problem. If you're asked to find the area, or if you're asked to find the total area, then you need to take the absolute value of the function. Okay? Now, another thing to recall, and that's going to come in handy whenever you are integrating absolute value types of things, is this fact here. So, and we talked about this again. I think it was in 5.4 that we talked about this. But the integral from a to b of f of x, turns out that that's the same thing as the integral from a to c of f of x plus the integral from c to b of f of x, you know, where c is some point in the middle. And so you can chop this up into little subintervals and then just add up the results. Now, why is that useful? Well, let's take a look at a couple examples. Okay, so let's find both the net signed area and the total area, so that we're perfectly clear on the difference between these things. So let's do that between f of x equals 1 minus x squared and 0, 2. Okay. So the net signed area, I'm just going to abbreviate it, NSA, right? So net signed area, well, that's just the integral from 0 to 2 of f of x, 1 minus x squared dx. Okay? Let's see what we get. That's going to be x minus x cubed over 3 evaluated from 0 to 2. So that's going to be 2 minus 8 over 3 minus 0 minus 0. Okay? 2 is 6 over 3, so 6 over 3 minus 8 over 3 should be negative 2/3. So you get negative 2/3 when you're looking at the net signed area. Now, on the other hand, if you're looking at the total area, which I'll abbreviate TA, well, that's going to be the integral from 0 to 2 of the absolute value of 1 minus x squared. Okay? Now, a picture is worth 1,000 words here. Let's see if we can figure out what exactly is going on. If I think about a graph of this function from 0 to 2, I know that this is a parabola that opens down and it's been shifted up 1 unit. So it's going to look something like this, and then, oh, we go down 1, 2, 3, 4, right? It's going to look something like this. Okay? That's what f looks like. So the absolute value of f is going to reflect all of the negative stuff up above the x-axis. So it's going to look, right here, the absolute value is going to cause this to bounce back. Ooh, how does that look? So it's going to bounce back kind of like this, right? That's what the absolute value is going to look like. But what that suggests to me is that we should split the integral right here at 1. Okay? We should split the integral at 1. From 0 to 1, I'm just going to integrate f of x, 1 minus x squared. From 1 to 2, I'm going to integrate the negative version, because that's where this thing got reflected, right? So I'm going to integrate negative 1 minus x squared. Okay? So this is going to be the integral from 0 to 1 of 1 minus x squared dx, plus the integral from 1 to 2 of negative 1 minus x squared dx. Okay? So I'm splitting at 1. I'm splitting at 1 because that's where the thing gets reflected. Okay. So, well, let's finish this. So I already found the antiderivative, right? This is x minus x cubed over 3 from 0 to 1. I'm going to just factor out, or take the negative sign out and say minus x minus x cubed over 3 from 1 to 2. And let's see what we get. So this is going to be 1 minus 1/3 minus 0 minus 0. Okay, minus 2 minus 8/3 minus 1 minus 1/3. Okay. Well, here I have a positive 1. So this is 2/3, right? Here I have a positive 2/3, and here, oh, I guess I'm going to get it's a negative and negative make another positive 2/3. So I guess that's going to make 4/3. Here I have 6/3 minus 8, negative 2/3, but this negative is going to make it positive as well. So I've just got a bunch of positive 2/3. I've got 2/3 plus 2/3 plus 2/3. Okay. So that's going to be 6/3, or in other words, 2. Okay. So the net signed area is negative 2/3. The total area is 2. So if you're actually looking for like what the real area is, in other words, maybe I can draw it in on the figure here, right? So the area that we were looking for was this, right? This stuff in red. That was the area that we're looking for. Well, if you do the net signed area, since these values are negative, it's actually going to compute this area, and then it's going to compute this area, and it's going to subtract the 2. And that's why you're getting a negative 2/3. So if you want to avoid that, then you have to make this one positive by taking the absolute value, right? And so that's what we've done here. And when you do that, you get 2, which is a pretty nice result, I think. Okay, let's do this for a different function. So let's do this for f of x equals cosine x and 0 to pi. And now I'll tell you what, it's not actually all that difficult to graph cosine x, but it's not totally necessary either, because what we really need to know is, where does the graph cross the x-axis, right? In other words, where is the graph equal to 0? Because that's where it's going to change from positive to negative. Or potentially, it could change from positive to negative there. So really all we need to know is, well, when does this thing equal 0? Because that's where I should split the integral, right? So cosine x, if you think about the graph, and I know I said I wouldn't graph it, but cosine x looks like this, right? It kind of goes like this and back up. So at 0, cosine x is 1. At pi, cosine x is -1, and it crosses the x-axis at pi over 2. So that tells me that's where I'm going to split the integral, right? The area that I'm interested in here is this. And you can probably tell that's pretty symmetric. So when I go to find the net signed area, I'm probably going to get 0, right? So let's see. Net signed area. Well, that's just going to be the integral from 0 to pi of cosine x dx. We did this antiderivative a second ago. It's just sine x from 0 to pi. I plug in pi. I plug in 0. Sine of pi is 0. Sine of 0 is 0. So we just get 0, sure enough, right? Not very interesting. But if I'm looking at the total area, well, that's going to be the integral from 0 to pi of the absolute value of cosine x dx, which turns out is integral from 0 to pi over 2, right? That's where the sign changes. From 0 to pi over 2 of positive cosine x plus the integral from pi over 2 to pi of negative cosine x dx. Okay? So this is going to be sine x from 0 to pi over 2 minus sine x from pi over 2 to pi. And let's see what we get. Sine of pi over 2, sine of pi over 2 is 1. Sine of 0 is 0. Sine of pi is 0. Sine of pi over 2 is 1. That's interesting, right? So you get 1 minus -1. That's 1 plus 1, or 2. So you get 2, right? So actually the area is 2. Well, that's kind of interesting that we got that. I did not do that on purpose, but there you go. Okay, another thing that I want to mention about fundamental theorem of calculus, part 1, is this. So the fundamental theorem of calculus requires that f be continuous on the closed interval from a to b. And to show you why it's important that we pay attention to that criterion, let's consider the following, right? So let's consider the integral from -1 to 1 of 1 over x squared dx. Now, you might be, if you ignore the criterion that f be continuous on AB, then you might say this. You might say, okay, I can find this integral. This is just x to the -2. So I'm going to add 1 to the exponent and divide by the new exponent. That's not bad, right? So this is just a negative x to the -1. If I plug in 1, 1 to the -1 is 1, and the negative sign will make it negative. So I get -1 minus, if I plug in -1, -1 to the -1 is -1, and then -1 times a negative will make it a +1. Holy schmoly. Anyway, so you should get -2 as the net signed area. But if you think about that, it doesn't make any sense, right? Because here's what the graph of 1 over x squared looks like. Okay, it looks something like this. Definitely you can tell that 1 over x squared is always positive, right? Because if you plug in a negative value, well, you're going to get a positive value out, right? So, you know, let's say that -1 is here and +1 is there. The area you're looking for is like all of this stuff, right? And it kind of goes up forever and ever and ever, I guess. So that's the area that you're looking for. It doesn't make sense for that to be -2. Okay? This isn't below the x-axis, so there's no reason you should be getting a negative number. So why is this happening? This is happening because we misapplied the fundamental theorem of calculus. This function is not continuous at 0. So note that f of x equals 1 over x squared is discontinuous at x equals 0. Thus, f is not continuous on the interval from -1 to 1. Therefore, the integral from -1 to 1 of 1 over x squared dx, or maybe we should say, therefore, the fundamental theorem of calculus doesn't apply to the integral from -1 to 1 of 1 over x squared dx, right? Okay, so we just need to be careful and make sure that what we're integrating is continuous before we try to apply the fundamental theorem of calculus. Now you may wonder, well, how do we take care of this thing then? And we'll talk about that. Okay, that'll be something that we discuss in a future section. Okay, to give you another example kind of along these lines, let's evaluate, or let's see if we can even evaluate this integral, 0 to 3 of f of x dx, where f of x is a piecewise function. It's going to be x squared if x is less than 2, and it's going to be 3x minus 2 if x is greater than or equal to 2. Okay. Now, given our previous discussion about the fact that f needs to be continuous on this interval, we could ask ourselves whether or not this is a continuous function. Now, certainly each of the pieces is continuous, but the question is, do the pieces match up, right, whenever the rule switches, right? So in other words, what is the limit as x approaches 2 from the left, and what's the limit as x approaches 2 from the right? And if those two limits match, then the function is continuous, right? So let's see, right? So we'll say limit as x approaches 2 from the left. That means I'm going to be plugging in something slightly smaller than 2, so I'm going to be using the top rule here, right? So it's going to be 2 squared, which is 4, right? Limit as x approaches 2 from the right of f of x. I'm going to use the bottom rule for that. So I'm going to get 3 times 2 minus 2, which is 6 minus 2, which is 4. So we'll say, since limit as x approaches 2 from the left equals limit as x approaches 2 from the right, and by the way, that's equal to f of 2. So since that's the case, f is continuous at x equals 2. And that was the only place where f could potentially not be continuous. Okay? It's pretty clearly continuous everywhere else. I mean, x squared is continuous on its entire domain, and so is 3x minus 2. This is just a parabola and a straight line. So the two pieces are continuous everywhere. The only question was, is this continuous where the rule changes? And the answer is yes, it is continuous there. That means that f is continuous on the interval from 0 to 3. So fundamental theorem of calculus applies, right? So we can say integral from 0 to 3 of f of x dx. A convenient place to split this would be right at 2, right? So that's going to be the integral from 0 to 2. Now if x is less than 2, we're using the top rule, so it's going to be integral from 0 to 2 of x squared dx. plus the integral from 2 to 3 of, if x is greater than 2, then we use the bottom rule. So that's going to be 3x minus 2 dx. Okay. So that's not bad. This is x cubed over 3 from 0 to 2. This one's going to be 3x squared over 2 minus 2x from 2 to 3. Okay, so we're going to get 2 cubed over 3 minus 0 over 3 plus 3 squared is 9 times 3 is 27. So 27 over 2 minus 6 minus 2 squared is 4 times 3 is 12. 12 divided by 2 is 6 minus 2 times 2 is 4. Okay. So the rest is just arithmetic, or that I don't particularly want to do because it has fractions in it. Well, okay, so this 8 thirds. 27 halves minus 6. 6 is 12 halves. 27 minus 12 would be 15. So this is 15 halves. 6 minus 4 is 2. 2 is 4 halves. 15 halves minus 4 halves would be 11 halves. So this is 8 thirds plus 11 halves. I could get a common denominator there. Multiply by 2, I get 16. Multiply by 3, I get 33. 16 plus 33 is 49 sixths, I believe. Check my arithmetic. But I know that I'm good up until this point for sure. Everything else, if there's a mistake, it's just an arithmetic mistake. So that's that. And that's all I want to say about Fundamental Theorem of Calculus Part 1. However, there is a second part. And it's a pretty cool thing, right? So Fundamental Theorem of Calculus Part 2 says, if f is continuous on an interval containing a point A, then the derivative of the integral is just the original function, right? Now the notation here is a little bit strange, but imagine, right? Imagine that a is just a number and that x is a variable. You integrate, so you find an antiderivative for lowercase f, and then you plug in x, which is a variable, and then you plug in a, which is a number. So you're just going to get a function out of this. You're going to get a function in terms of x. Now if you differentiate that function with respect to x, you get the original function back. Right? So that's Fundamental Theorem of Calculus Part 2. It's a little confusing to see it that way, but what I want to point out is that, as I said at the beginning of this section, this ties together the two main concepts of calculus, the derivative and the integral. And basically what this is saying is that differentiation and integration are inverse operations. So the derivative of the integral is the original function, and the integral of the derivative is the original function, right? So differentiation and integration undo each other. And because of the way that the topics were introduced, I don't particularly like the way that the topics were introduced in this textbook, to be honest with you, because of the way that they're introduced, it might seem obvious. Like, didn't we define it to be this? Well, we didn't define it to be. We didn't define them to be inverse operations, but it does just so happen that they are inverse operations, and it's pretty amazing, right? It's pretty astounding. If you think about what the derivative is the instantaneous rate of change, okay? Meanwhile, the integral is the net signed area. Why should those things be inverse operations of one another? Okay? At first glance, it doesn't make any sense. It doesn't seem like the two things should be related at all, and yet they are. They're inverse operations of one another. Formal proofs of this fact can be found. So the proof of Fundamental Theorem of Calculus Part 1 is on page 295, and proof of Part 2 is on page 300 of the textbook. You're welcome to go through those if you want. But for a more intuitive understanding, I would suggest you watch this video. This is a YouTuber, 3 Blue 1 Brown, and he does an excellent video about the fundamental theorem of calculus that I think gives a good intuitive understanding. In fact, I'm gonna put the video in this lecture, so I'll put the link together where I put the lecture in Canvas. But it's really a good video, and I think it would be possibly more instructive than looking at the formal proofs. Okay, but just to give you some practice with fundamental theorem of calculus part 2. Let's find the derivative with respect to x of the integral from 1 to x of t cubed dt. Let's find this integral directly, and then we'll note that it verifies what the fundamental theorem of calculus part 2 says, right? So let's do this, right? So integral from 1 to x of t cubed dt, that should be t to the 4th over 4 from 1 to x. So if I plug in x, I get x to the 4th over 4. And if I plug in 1, I get 1/4. Okay? Now, if I differentiate that, so I'm going to call this thing, oh, what should we call this? We'll call this f of x. Maybe I'll call it capital F of x. Okay? Now, if I differentiate, right, so d dx of this guy, I now know that that's just d dx of x to the 4th over 4 minus 1/4. I guess I didn't need to label it after all. But now if I find the derivative is, well, I'm gonna take the exponent down. 4 times a 4th is just 1, and then I subtract 1 from the exponent. I'm gonna get x cubed. And derivative of 1/4 is just 0. Oh, so I just get x cubed. Well, look, it's the same thing, just with a change of variables, right? But it's the same function. So that's exactly what fundamental theorem of calculus part 2 says will happen. And you may think, well, but what good is that to know? Well, it's good to know, for one thing, that integration and differentiation are inverse operations of one another. But for another thing, if you happen to have a function in here that you didn't know off the top of your head what the integral was, like, oh, I don't know, let's say that you had something like this. Something like e to the x squared dx. That's not something that we can integrate. Not even with a u substitution can we integrate this. Well, okay, so I should be careful. It is integrable. You can integrate it, but not with any of the techniques that we know so far. Sorry, let me change the variable here. But the good news is that we don't need to know how to integrate it, because we're just going to turn around and differentiate it after we're done integrating, and we know that those two things are inverse operations. So this should just end up being e to the x squared, right? Without you having to do any work at all. So it's kind of nice for things like that. That's all I have to say about fundamental theorem of calculus. It's a really, really cool result.